Okay, so now our areas and volumes are going to be behind us for a while. But remember, we have done, so far in this unit, come on, we did measurements and conversions. And with our measurements, we did adding and subtracting. Multiplying and dividing measurements. We did converting measurements. Converting, of course, is going to be the big one. We've done angles in this unit. So make sure you're familiar, remember how to do the angles, finding missing angles and all that good stuff. And then we've done areas, volumes, and surface areas. Today we're moving into the final section of this fourth unit, and that is statistics. To give you guys a little bit of a side note, I will not be here this coming Thursday. So what is that, the 11th? I won't be here. I'll be in New Richmond. I'm on an interview committee to rehire one of our positions we're trying to fill. I will be here Wednesday, so we'll have lecture on Wednesday. Thursday, what I will do is I will actually post to Blackboard a video review. Because remember, our Unit 4 test is next week, Monday. So that's going to be May 15th. Is our Unit 4 test. So that'll give us then Wednesday and Thursday. I've considered moving that back till next week, Wednesday. It's a possibility. The only problem is Monday's a 2-hour class, and Wednesday's only a 1-hour class. I'd rather give you the 2-hour class, but I'm considering moving that back to the 17th, but we'll see how things go over the next couple classes. And we'll see what your preference is come Wednesday, if you'd rather move it back or not. The option, if I moved it back till Wednesday, is we'd probably not do the final test. And remember, the final test isn't to evaluate you, it's to evaluate the class. So the final test, if we do it, can't hurt your grade, it can only help you. If you do like really well on it, I'll average in with your score to increase your grade, but I won't let it hurt your grade. But that's an option, is we might consider moving it back. But I will, on Thursdays, I'll post a video review for that test. Yeah, we'll know on Wednesday. We'll discuss whether we're going to keep it scheduled for Monday, if we'll push it back till next week, Wednesday. Depends on how much we get through in the next couple of classes. And how much you guys are enjoying statistics. I'm sensing a little cynicism there. Maybe a little bit of prejudgment on their account. Okay, so let's take a look here. Statistics always gets lumped into math, and it uses math, but it really isn't a math course. None of the math involved in statistics is really upper level math. It's all pretty basic math. What statistics is one, it's a set of vocabulary. It's almost a foreign language. We're taking words that you've heard before, but applying them in a slightly different meaning than what you might be used to using them in. And second, it is organization. So you're taking numbers and you're organizing them in a certain way to make them easy to interpret, easy to draw conclusions from or read. and also summarizing, I should put in with organization. You're summarizing it so you can get an idea of a lot of numbers really quickly. And finally, decision making or analysis, or however you want to put that. Most people use numbers for making decisions, but don't have really an organized way of doing it. And statistics actually defines an organized way of using those numbers to make a decision. A lot of times, just because one number is bigger than another number doesn't necessarily mean as much as most people think when they look at them. It has to be enough bigger to really prove they're a difference. So when we're dealing with statistics, we have to deal with a lot of vocabulary. So the first thing I want to define is a population. And a population can be people, or it can be objects. But it is the group that we want to learn about. Or make a decision about, one of the two. Something smaller than a population is called a sample. And what a sample is a smaller group chosen from the population. And the most basic concept in statistics, the most basic construct in statistics is choosing that sample and how we choose that sample. But first, let's talk about why we choose a sample. And I should qualify this for a large population. For example, if I wanted to learn about WITC students, there's roughly, between the 4 locations, 1,200, I believe, WITC students full-time at any one given time. 1,200 is not that large of a number. We can survey, or we can gather information from pretty much all of those students. So if our population is WITC students, we really don't need to take a sample. We can actually get to the whole population and gather information on them without too much difficulty. So a sample really only applies when there's a relatively large population. Like Sands Club members or something. Yeah, exactly. There's a large population of people that use that, so it would be hard to get information from all of them. Also, we use it when there's no other construct. Now, you mentioned Sam's Club. A lot of times to get a membership at Sam's Club, you've got to go through an application. Now, they've loosened it up. Non-members can go to Sam's Club now. It used to be, 5-6 years ago, I think they changed it. It used to be you did not have to be a member to go to, or you had to be a member. You actually had to be a small business owner of some sort, or to be on a small business's membership to use that store. They've changed it now so anybody can use it. They just don't get as much of the discounts. But when you had to be a member, you had to fill out that application and you had to renew it every couple of years. They asked a lot of information on that application, so they knew the information about their members. So even though they had tens of thousands of members, they knew the information because they had this process of gathering the information, and it was put in a computer system, so they had it. So they didn't need to take a sample. They already had that information from everybody. So it's when you don't have some other construct, some other source of that information where it's already there. If you need to actually try to gather that information is when you need a sample. So the reasons why we use a sample. Number one reason, it might be arguably 1 or 2, is the time. If there are too many people or too many objects, you don't necessarily have the time to get the information from every person or from every object, measure every object. You know, if you have a factory, the assembly line on this factory that's producing 12,000 parts, pieces per day, you don't have time to go through and measure 12,000 pieces to make sure they're all exactly proper. So you choose a sample. You might choose so many of those to measure to make sure that they are at the specification, and then hope that the rest of them are there. So the amount of time is a factor. Now, along with, there's other time-sensitive factors that we'll come to in just a second. But probably the second big reason, and again, time 1 and 2 are interchangeable here depending on what your priority is money. It can be kind of expensive to gather information. If you're looking at people, if you're sending out surveys through the mail or whatever, or even over the phone, phone bills aren't as big of a concern anymore. 30 years ago, you paid by the phone call or by the minute, so it was more expensive. Now, most phone plans are unlimited, as long as you don't call outside a certain area or call international or anything like that, there's no extra charges. So the phone bill itself is no longer a huge consideration, but you still have to pay somebody to make that phone call. So there's an expense there. Or if you're sending out surveys, you have postage expense, paper expense. So you take a sample to make it smaller to save costs. Now back to the time issue. Or if you're measuring those parts, again, you have to pay somebody to measure those parts. Their wages can get expensive as well. So money is, like I said, time and money are usually the top two, and what order they're in flip-flops depending on your priorities. Changes over time is one of them. If you're looking at people and gathering information from people, so doing a survey, you have to be able to gather that information quickly. That period of time is called a window. You must have a reasonably short or reasonably small window that you're gathering that information in. If you're doing a political survey, for example, you're trying to do a survey on whether you favor this candidate or not, if you approve of this candidate. Well, if I can make all those phone calls in one day and talk to those people and gather their opinion, that's a reasonably small window. If I have to spread it out over a week, okay, that's questionable. But if it's going to take me a month to gather this information, that's most likely not acceptable. Things happen all the time that change opinion. So let's say it takes me a week to gather this information. I start on a Monday and I'm going to finish on a Friday. Let's say on Wednesday this person goes on television and says something really stupid, or does something that just upsets a whole bunch of people. Well, some of those people that I called on Monday that said they favored this person, they approved of this person, may not approve of them anymore. So the conditions under which I'm gathering that information have changed. So that's the reason why the changes over time, that reasonably small window, is important, as we must gather under same conditions. We call that uniform conditions. Things happen over time, and if we're spreading out gathering that information over too long of a time, things might change. Even in the factory setting, if we're gathering information on those parts we produced, things may have changed in the machine. One of the jigs on the machine may have moved or whatever, rattled loose, or got a speck of dust in it, or something in it that set it off so it's not working right. So all the parts may not be produced under the same conditions. In fact, there's a whole branch of statistics called statistical process control, quality control, that actually helps track that and catch those changes. If something gets bumped and moved on a machine, or a piece of metal or something gets stuck in there so parts don't line up when they come into the machine as well. it's a process for catching those before you've produced thousands of parts. You can catch it after only maybe a couple hundred parts that something's not looking right here or something. But those uniform conditions are big. You don't want to spread it out over such a big time that you're not gathering them under the same conditions. I'm going to put unobtainable. Unobtainable can be a couple of different things. First, I should have put difficult to define, but can't define the population. For example, let's say there's an election coming up, and I want to conduct a survey to try to predict who's going to win the election. Well, I've got the same problem I did up here. Candidates are saying stupid things all the time to change your opinion. Or they might say something just wonderful that changes their opinions. But unobtainable, trying to define that population. Well, the population we're really looking at, we're not looking at all eligible voters. What we're really looking at is people who will vote in that election. Well, there are people out there that, 2 weeks before the election, they don't know whether they're going to vote or not. So how are we supposed to know if they're going to vote, whether we include them in the population or not? So that's one of the reasons to take a sample, is sometimes you can't define what the whole population is. And second, just non-cooperation. Every 10 years, the United States government sends people out to do a census, trying to gather information about every person in the whole country. Well, every 10 years, every time they do this, there are people that refuse to respond. They actually send people out to your homes if you don't respond and try to gather information from you. But they've never achieved a 100% census. They've never managed to gather information from every household in the country. It just doesn't happen. You can't do it. So in many cases, it's just not possible to get information from the whole population. The final one that I'm going to mention here, the final reason for doing a sample that I'm going to mention, is a little bit different from the rest of them. But it's a very big reason in manufacturing, and that's destructive testing. Obviously, it's not going to apply to people if you're surveying people. But if you're testing parts, let's say you have parts that you're producing for something that need to meet a minimum strength requirement. So let's say you've got that part, and it has to be able to hold a certain amount of weight. So you take that part, you put it in a machine, and that machine pulls on it until it breaks, and it measures how much force it took before it broke. Well, if you test every part, you've broken every part, you've got nothing left to sell. So if the testing requires it to destroy the part to test it, you can't test every part. So you have to decide, how many of them do I have to test to balance out being sure that the quality is being met, but also having enough parts to sell to make a profit. You don't want to test too many of them, or you're destroying your profit margin there. So now I mentioned two big terms there. I mentioned census. And census is an attempt to gather information from a population. Along with a census, I'm going to use a term called a parameter. And a parameter is information describing a population. A parameter is a little bit fuzzy. A parameter may not necessarily be something that's been gathered, where you actually gathered information from every member of the population to find it. It may have been that you gathered information from a survey and made a conclusion about the parameter. It's still a parameter. You're still describing a population with that information. So I use the word survey. What does survey mean? Well, a survey is an attempt to gather information from a sample or about a sample. And along with a survey, we have statistics. A statistic is information gathered from the sample. A lot of times that statistic is used then to estimate that parameter about the population. So there are two types of statistics. There's descriptive statistics. In descriptive statistics, we're gathering information from a sample in an attempt to describe the population. So we might be gathering information, and we might, if we want to know the average number of hours that a student at WITC works outside of class on their homework. Like I said, it's a relatively small population. We maybe could do the whole population, but maybe you decide to take a sample. You take a sample, you gather information from them, and the average student's working 35 hours a week on homework outside of class. So then we'll use that then to describe, hey, we figure from this sample, we estimate that about 35 hours a week is what students spend outside of class on homework. So you're just trying to describe or summarize the population. Inferential statistics is an attempt to draw a conclusion. Or make a decision. You might be comparing two products and trying to decide which product is better, or happens in the pharmaceutical market all the time. You're testing new medications, new drugs. Is this new treatment better than the old treatment? And there's a process, a statistical process you go through to test that, to draw that conclusion. For this course, we were going to be focusing on descriptive statistics because we only have a few hours to work. If we had several weeks to do statistics, we get into the inferential side of it. We just don't have that kind of time. So now we're going to step back. Talking about these descriptive statistics, we're going to look more at sampling. Now again, if we had more time, we would talk about types of samples and different ways of selecting a sample. We don't have that kind of time, and it can be kind of complicated. And I'm not going to, on a test, ask you what type of sample was this or what type of sampling method is used here. But we should know that there are two requirements of samples. One is it has to be an adequate size. Now, adequate size can mean a lot of different things. A size can actually be too big. You want the population to be at least, depending on the type of process you're going to do, sometimes they say 5 times the size of the sample, sometimes at least 10 times, and in different processes, 20 times the size of the sample. So your sample has to be, the population has to be large enough that you can take a sample from it. Basically what they're saying is if the sample is more than 5, 10, or 20% of the population, you should just gather information from the whole population. Or it can't be too small. If I want to know how many hours a week students spend on tests or on homework outside of class, I could ask the students in the room right now. Well, there's 3 of you at the moment. That would be a very small sample, and it actually violates the second thing here as well, that it has to be randomly selected. There might be reasons why you're in a particular class. There might be common traits that you have in this class. Now, this class is for all different programs, but a lot of my classes are program specific. The class that just left here is all for CNC machine tooling students. Well, there might be, those are students who like to work in the shop. And in many of their classes, they have work time in the shop. So most of their work is completed in the shop. So they're not going to spend as much time outside of school doing homework. But they also have more hours in the classroom during the week because it's expected they're going to do more of their work in the classroom. Whereas a business student may only have 16 or 18 hours of class in a week, but they might be expected to do 30 to 35 hours of homework outside of class. A machine tool or CNC student might have 30 hours of class in a week, but only be expected to do 5 or 10 hours of work outside of class each week. So that might make a difference. I can't just say, hey, I'm going to ask the class that's in the room right now. That's not random. Random means every member of the population has an equal chance of being selected. So I said we're not going to spend any more time talking about adequate samples. We have to make sure it's big enough, but not too big, and that it's random. I said I can't just go out in the hallway and ask the next 40 students to walk by my door because I'm on this end of the building. Most of the business students are on the other end of the building. Here, most of the shops are at this end of the building, so I'd be talking to a majority of trade and technical students. So you have to have a process that, and of course, students at other WITC campuses would have no chance at being selected. Or students that don't have Monday morning classes wouldn't have any chance of being selected. So you have to make sure that every member of that population has an equal chance of being selected. Political surveys make this mistake all the time, by the way. I know this is 2017, and most of us can't imagine not having a cell phone, but there are still households out there that don't have a phone at all. So if you're doing a phone survey, well, those households that don't have a phone, there's no chance they're going to be selected. So there's flaws with every process. So this is one of the things in statistics is you can't be perfect, but trying to limit those imperfections. So anyway, let's talk now about summarizing data. Data, first of all, is information gathered from either a sample or a population. Usually, of course, it's going to be a sample because we don't want to try to gather from the whole population. There are 2 main categories of data. Depending on what textbook you're using. One type is called qualitative, or sometimes called categorical. I think categorical is a better name for it. What it is it's your answer puts you into a category. All of of statistics, gathering information is about asking questions. The answer to your question is your data. Now, if we were in a formal statistics class, we'd talk about your random variable and all that stuff. And well, we're not really, the answer to the question is your random variable, but we're just looking at some of the basics here. So you're asking this question, does the answer to that question put you into a category? Any yes or no question is going to be categorical or qualitative. You know, did you vote for this policy at the last referendum? Yes or no? That puts you in the category of voting for it or not voting for it. Do you own an SUV? Again, yes or no. Any other question where the answer is a category is qualitative or categorical. What's your favorite color? Would be categorical. They put you into a category depending on your color. Sometimes it's easier to define qualitative or categorical as the opposite of this next one, which is quantitative or numerical. Obviously, numerical data or quantitative data, the answer to that question that's being asked is a number. Now, quantitative data qualitative data can be broken up into subcategories, but we're not going to talk about those. Quantitative data can also be broken into subcategories. First one is what's called discrete numerical data. Discrete is counting. How many children do you have? Well, you're going to count 0, 1, 2, 3, 4. How many cars do you own? Same thing, 0, 1, 2, 3, 4. That's discrete. The next is continuous. Continuous is measured. How tall are you? Well, that's going to be measured. How much do you weigh? Again, that's a measurement. Continuous, the technical definition of continuous is no matter how close together two numbers are, you can always find a number in between them. Think about measurement, same thing. No matter how close you are to the height of another person, there's always a chance you can find somebody that's in between you in heights, because you can break it down to small. You have to choose your level of measurement on continuous, but you could break it down into smaller and smaller units. No matter how small you get, you can always break it down into smaller units if you wanted to. Whereas discrete, you cannot. So some of the biggest arguments usually come like with age. Is age discrete or continuous? It depends on how you define it. If you ask your age as in, if you define age as in how many birthdays you've had, that's discrete. You're going to count how many birthdays you've had. If you're defining age as a unit of time, well, yeah, you can be alive so many years, so many days, so many seconds, so many milliseconds. You can break time down into smaller and smaller units. It just matters how you want to define them and how you want to round it. So age is always kind of an argument on how you define it. The other one that's always an argument is money. Is money continuous or discrete? Well, if we're using the US dollar, we break it down to a penny. And yeah, we can do calculations that come down to a decimal or a fraction of a penny, but we still always round it to the nearest penny. So in my book, we count money as being discrete because you can count it. So even though you're doing all these calculations with it, it is always in the end rounded to the nearest cent. But there is some gray area there. So to organize data, it depends on which type of data we are looking at. Is it categorical or qualitative, or is it quantitative, numerical? And even within the numerical, discrete versus continuous makes a difference. So we're going to start out talking about categorical or qualitative. I'm just going to use the term categorical for now because to me, I think that's easier to understand. And I am never going to ask you to look at a variable and describe it. Is this categorical or numerical or qualitative or quantitative? So if we're looking at categorical data, again, the answer to that question puts you in a category. So I might ask, what is your favorite color? In fact, I might randomly select, I don't know, let's select several students and ask what their favorite color is. So let me make a list here. And we're going to limit our list to red, blue, and green. So of those three, which color do you prefer? And so let's make our list. I'll get rid of the commas. What do I have there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, we'll make that work. So there we've got 50 answers, R, B, or G, depending on what color they chose. Looking at that list, can you tell me which one was chosen the most often? You think red? Well, if I look at this, it depends on where we focus. Psychology of the human mind, the average person can actually focus on between 7 and 13 items at a single time. If you try to see more than that, it's tough. You tend to lose track of some. So if I'm focusing right here, what color appears to be the most common there? Blue appears to be common. If I'm focusing right here, what color appears to be the most common? Green. And if I'm focusing over here, definitely red. So it depends on where we're focusing. To make it easier, we organize it. And the first tool we usually use from raw data, and this is what we call raw data, just the numbers or the responses listed out. The first tool we often use to organize this is called a frequency table. And in a frequency table, we list out all of our possibilities. So here it's color. And we're going to list out red, blue, and green. Now again, if this were a longer course or a longer unit on statistics, I would really stress this point that it doesn't matter what order I put these categories in. Red, blue, green, blue, red, green, blue, green, red. There is no logical order for them, so I'm just putting them in an order. Now, normally, the next column would just be frequency. But now, since I have the raw data here, I'm going to insert a column. It's a working column. I'm going to call it the tally. It's to help me count this up. So let's see, I've got red, blue, blue, red. Red, blue, blue, red. green, red, green, green. Green, red, green, green. Blue, green, red, green. Blue, green, red, green. Red, red, blue, red. Red, red, blue, red. The prediction of red's looking pretty good so far. So blue, green, blue, blue. Blue, green, blue, blue. Red, green, blue, red. Red, green, blue, red. Green, green, blue, green. Red, green, red, red. Red's still in the lead. Blue, red, blue, red. Green, red, blue, green. Green, green, blue, red. Green, green, blue, red. Red, green, red, red. And blue and red. So looking here, red has 20, blue has 14, and green has 16. So red did come out more often. But that might be closer than what you would have expected. Usually I do better. Usually I get them like all within 1 or 2 of each other, really close. But still, 20 versus 16 is not that big of a lead. So now that we have them organized in a table, we definitely know which one was the most common. And like I said, most of the time we don't have that tally column. We would redo this table like this. So we've got red, blue, green, 20, 14, 16. That tally column is just a working column to help us construct the table. When we present that data, we would take that out because it's not attractive. Now, from this frequency table itself is useful, but sometimes we add a column to it that we might call relative frequency. Relative frequency is what portion of the whole amount is each of them. To find relative frequency, first thing we have to do is find a total. So the total here, if I add all those up, is going to be 50. So the relative frequency is the raw frequency divided by the total. So here it would be 20 divided by 50, or 0.4. Here it's going to be 14 divided by 50, or 0.28. This will be 16 divided by 50, or 0.32. Now that relative frequency better add up to 1. Now with round off errors, we divided by 50 here, so we got nice, neat little decimals. But if it was like 46 or 60 something, you might have some ugly decimals. Round off error, it might come out to be like 0.999 or 1.001. And that's okay, but it should be really, really close to 1. And we could also define a percent frequency. I ran out of room here. A percent frequency would be pretty easy. This would be 40%, 28%, 32%. It's just moving the decimal point over 2 spots from that relative frequency. So relative frequency and percent frequency are really the same thing. It's just a way of expressing it. Relative frequency, you're expressing it as a rate, and percent, you're expressing it as a percent. It's just a matter of moving the decimal point. So then the next step is to graph these, to construct a graph from this table. Now we're up on break time here, so let's take our break. So now that we've organized the data in a table, with qualitative data, categorical data, we have a few options. The most common option is a bar graph. A bar graph can either be vertical or horizontal. In statistics, we tend to favor the vertical bar graph. In media, they tend to do a lot of the horizontal ones, and I'll show you both. In a vertical bar graph, the bars go vertically. So the categories go along the bottom. So we'd have red, blue, and green. And of course, we have to label that as favorite color. And of course, this is going to be frequency. And we have to make sure we label this axis so that it goes up to the highest number. So the largest number is 20. We have to make sure that axis goes up to at least 20. So we're going to go 5, 10, 15, 20. Notice we don't have to count up by ones. We don't have to mark every little mark. It's possible that we'll estimate in between here. So red was 20, so we're going to go up to 20. Blue is 14, goes up like that. Green is 16, goes up like that. Now we can look at this graph and very quickly tell you red was the most common. And we can also very quickly say blue is the least common. And we can compare. If I asked which had more, blue or green, well, green's bar is taller. So the bar graph and any graph, its major strengths are to figure out finding which one has the most or the least, or comparing to. Now, because these are relatively small numbers, if I asked you how many selected blue, well, you could probably come in here and pretty accurately say, well, just under 15 or 14. But if these were, 100 and 150 and 200 instead of, 10, 15, and 20, it would be difficult to tell, is that 140 or 141? So finding exact numbers is a weakness. If you wanted exact numbers, you come back up to the table and you get the exact number off the table. But looking at this table, if I asked you which one was the most popular, well, there's only 3 categories here, so you could relatively quickly find that red was the most common, most popular. But if I had like 10 different choices of color, it might take you a while to pick out which one's the largest number. Whereas on the graph, even with 10 different categories, you could pretty quickly pick out which bar is the tallest bar. If it were a horizontal bar graph, the categories go on the side. And again, you would label these favorite color. And on the bottom would be your frequency. So here's another way of labeling. You can see I did small marks in between. I didn't have to label every mark I put on there. I marked every one, but I only labeled every other one, or I could label every 5th one or whatever. So red goes up to 20. Blue goes up to 14. Green goes up to 16. Now, I did something on purpose here. In fact, I'm going to make it a little bit more obvious. We'll reverse it a little bit here. Looking at this, what's a little bit odd about this graph? Comparing the red to the green. The bar for the green is much wider, isn't it? Now I did it here so the shorter bar was wider, so it's not quite as prominent. The red is still longer, and really all that we're concerned with here is the length. The red is longer, so there's more red than there's green. But that wider, especially if this was done in color, let's say I colored this one in green, and I colored this one in red. Looking at this, I see more green than I do red, don't I? So there's that psychological effect. And that's actually one of the biggest things that's done in statistics. Psychology actually plays a big factor in statistics. And people that use statistics for public manipulation, I guess is the blunt way of putting it, like advertising. Let's face it, advertising is about manipulating a consumer group, getting them to do what you want them to do. This is one of their strategies. By making the green one wider, even though it's shorter, it looks bigger because you see more green, so the difference doesn't stick out. Had I done this the other way around so that the red one was wider than the green one, it would look like the red one was much bigger than the green one because it's wider. Like I said, I did it this way intentionally so it was the smaller one that was wider. Another thing that can be done is this. I'm just going to use R, B, and G here, and I'm not going to label that as favorite color just to save time. So here's red, here's blue, here's green. Now I was careful to try to make them all the same width this time, but you can still see there's a magnified difference here. This is very accurate, but the red looks like it's like 4 times as big as the blue and twice as big, more than twice as big as the green. Why is that? Well, because of this right here. Because of that, we're not starting at 0, we're starting at 14 and numbering up. So we've left off this section of the graph here. Now there's a purpose for this type of graph. It helps us make it easier to see the difference between them, but it also can be deceiving. Even though red here clearly shows it's a little bit bigger, this makes it look like it's 3 or 4 times as big. So it can magnify those differences. Yeah, it makes it look like there's a way bigger difference than there is. It's meant the person or the company or whatever that's the larger one would use this graph to make it look like they're really dominant compared to everybody else rather than just barely beating them. I mean, there are some I've seen that used where there's companies that are competing where sales might look like this. Realistically, all pretty even, but when you cut that out and you do it, it might look like that because you've taken out all of this and it really magnifies those differences. Like I said, very deceiving. It all depends on what side you're on. I mean, they said there's a purpose for this. It makes it easier to see the details. It's very easy to see that that's 14 now and this is 16. But if you're not paying attention, and even if you are looking at the numbers, you might read the numbers, there's still that psychological effect of this looking. If somebody asked you if there were a lot more people that chose red than blue, if I'm looking at this graph, I'd say, nah, there's a few more. Here I'd say, oh yeah, there's a lot more. Just the psychological effect of it. Okay. Yeah, that's the Woods group. So another graph, don't do this to me. Oh, there it goes. So now the next step then, the next type of graph we're going to look at is a pie chart or a circle graph. And technically there is a difference. A pie chart is for categorical data. A circle graph is for numerical data. But let's go back to our table here of color and frequency, where we had red, blue, and green, 20, 14, and 16. And if you recall, we had added that column for relative frequency, which was 0.4, 0.28, and 0.32. And we said we could convert that into a percent frequency. So just 40%, 28%, and 32%. For a pie chart, this is what I want. If you don't remember how I got that percent frequency, or the relative frequency is the big one, go back and look. Remember, I had to find the total of 50, and then each frequency had to be divided by that total. So when we do a pie chart, that's what we're graphing, is that percent. Now, if this were 30 years ago, we'd go through and we'd say, okay, a circle is 360 degrees. We'd find 40% of 360 degrees, then we'd take a protractor and measure out that angle. We're not going to do that. Now, Microsoft Office, Microsoft Excel has programs that will very quickly spit out these graphs and do them perfectly. So we don't have to be that precise by hand. So right now, for our purposes, we just want to do basic rough sketches. And to do that, we're just going to look at, okay, half of a circle is what percent? 50%. And a quarter circle is 25. And if I cut that in half to an eighth of a circle, that'd be like 12.5%. So if I'm looking at this, blue is 28%. That's a little bit bigger than a quarter circle. Probably something like that. That's blue. Green is 32%. That might be. Let's look at the red is 40%. Well, 50% minus 12.5 would be 37.5. But remember, this is a little bit bigger. So this is really 50% minus 9. That's about 40%. So I'm going to go straight up with this. So you see, this is a little bit less than half a circle over here. That's my red. That's not going to work out real well, is it? Nope. All right, a little bit less than that. Got to be somewhere like in here. That's my red. Then this is going to be green, a little bit bigger than the blue. I can see that's not perfect. I did a lot of estimation there, but it works out. Red is definitely the largest. Blue is just a little bit bigger than a quarter. Green's a little bit bigger yet to get the 32%, and red is almost half a circle. Now, just to show you how simple it is in Excel if you wanted to make these, we're not going to require you to do them in Excel, but just to give you a little look at it. Oops, come on. Just go to the insert menu, pie chart. There it is. Now, right now I've got everything out here, but I can make it smaller. Get rid of that little key. Now the colors are, you can actually go through and custom edit the colors, because right now red is blue and blue is red. But you can add data labels like that tells you how much. So this is 16. You can do all sorts of other things where you can format the labels. You can include the series name, the percent, like that. So it puts the frequency in there. I'd have to change some of the labeling a little bit to make it work, but you can see it's all in there. This is an Excel class, so I'm not going to go through how to adjust the labels and all that stuff for you. But you can see it gives you a perfect graph pretty quickly. And like I said, you can custom click on each one and change the color of each slice so it matches the color in a case like this to make it a little bit more effective. So that's our graphs for categorical data. Now, there's a graph I'm going to mention here. I mention it with a grain of salt because I hate them. It's a pictograph. It's a picture graph. Pictographs are meant for dramatic effect, and which means they're not horribly mathematically accurate, statistically accurate, and in many cases, they're a great tool and used in deceiving. You know, we talked about that whole deception in statistics, which is a big thing. One of my favorite quotes on statistics was Mark Twain. And pardon the language on this one ahead of time, but Mark Twain once said, there are lies, there are damn lies, and then there are statistics. And there's truth to that. I mean, you can use statistics to say whatever you want to try to make them say. So anyway, a pictograph is one of those tools that's often used to try to make a statement. Like if we wanted to look at how you got to work today. You might have walk, car, or bus. And let's say that there were, I'm going to keep these numbers small just to make this easy on me. 12 people that walked, 16 people that drove in a car, and 24 people that rode a bus. So I have a little key over here that says that's 2. So my walk, to get my 12 people, get 6 of them. And yes, that is the extent of my artistic ability. So that's my 12 people for walking. For car, that might equal 5 people. Yeah, but I'm ashamed to say it took a lot of practice to get to where I could even draw them that well. Now that's 15 and they need 16, so something like that. Cut off the back end of a car. Bus is 24. Let's say that equals 10 people. That's 20, so I need 4 more. Might be something like that. Now looking at this, you can see that this doesn't necessarily line up here. I mean, yeah, this one's longer, but it really should be twice as long as this one. So the length doesn't necessarily line up. It's the number of pictures that's really important. Now a good picture graph, not only will the number of pictures work, but the length will also match up. So I mean, I purposely did this one a little sloppy. This is an accurate picture graph, but it's not, it's deceiving. You got that psychological effect of the size doesn't match up with the numbers. That's all I'm going to say about picture graphs because, like I said, I don't like them. And there are things that are kind of done to hybrid picture graphs with other graphs, like with bar graphs. Like if I want to compare A and B, I might do a bar graph like this. You know, I mentioned that the width of the bar. Well, A is just a little bit bigger. All that really matters here is how it lines up here. A is just a little bit bigger than B, but because it's wider, it makes it look huge. And they can add in even the third dimensional effect like this. Where B looks like it just totally or A looks like it totally overshadows B. But again, all that matters is the height. So there's a lot of things that are done with those picture style graphs that are really, really kind of deceiving. If we look at numerical data, there's a couple of different ways we can organize it. If we're dealing with discrete data, it depends on the number of different possible values that there are. Let's look at number of cars owned. And let's say that we have responses that range from 0 up to 4, and that nobody that we surveyed owned more than 4 cars. Now, I'm not going to go through the process of writing out the raw data and putting it into the table. We're just going to give you the table. So let's say that we had 4 people surveyed that had no car, 37 people surveyed that had 1, 23 that had 2, 5 that had 3, and 1 that had 4 cars. So there's our set of data. Very, very similar to our frequency table we had for the categorical data. If we have discrete with a large number of possibilities or continuous data, we can't list individual values like this. We have to do ranges. And those ranges are usually referred to as classes. So let's say we're looking at height and frequency. So let's say we measure the height of several people, and we go down to the 1/10 of an inch. Well, you're not going to list out everybody's height, every possible height from the smallest to the largest by the 1/10 of an inch and get a frequency for each one. Because chances are there's no 2 people in that group that were the same height down to the 1/10 of an inch, or no more than 2 or 3 at most. So rather than doing that, we might list out, let's say our shortest person is 4'10". So we might start out at 58 inches and go up to 61.9. Then we'll go from 62 up through 65.9, and 66 through 69.9, and 70 to 73.9. Let's say nobody in our group was taller than 6'2". I'll be realistic. We'll go one more. Let's go 74 to 77.9. So those are our heights. And let's say we only had one person in that height range. 6, 19, 17. What's that come out to be? 36, 42. Put 7 in that range. So those are, so now when we look at this, here, we know there's 37 people that have exactly 1 car. Here it's not so exact. There's 6 people that are falling within that range. But it just wasn't possible to list out every possible value. So we can graph these as well. It's not called a bar graph anymore. For numerical data, it's called a histogram. So in a histogram, it's always going to be vertical. So our heights are going to be listed across the bottom here. Now, I'm doing this one over here, obviously. So we're going to list 58 to 61.9. Now, why did I go 61.9? Well, because I can't go 58 to 62, because then the next one would be 62 to 66. If somebody comes in at exactly 62.0 inches, which group do they go into? So you can't have overlap. I had to go 58 to 61.9 because I'm going to the 1/10 of an inch. I also can't leave gaps between them. I can't make it possible for someone to have a height that's between those groups. So 58 to 61.9, 62 to 65.9, 66 to 69.9, 70, 73.9, and 74 to 77.9. So those are my classes. And up the side, I have to have my frequencies. I have to go up to at least 19. So I'm going to go 5, 10, 15, and 20. And when I draw in these bars, this one goes up to 1. So look like that. The next one is 6, 19, 17, and 7. What do you notice about these bars that's different from the ones I made for the regular bar graph? To remind you, we'll go up here. Oops, that's right, the bar graph, the Word document shut down. The bar graph we had, red, blue, green, looked something like this. The first thing you notice is there's space between the bars here. Here the bars are tight together. Why is that? Well, remember, I had stressed to you that there was no set order that these colors had to be, and I could put them in any order. And that's true. I could have green first, blue first, red first. It doesn't matter because there's no logical order for the colors. For the numbers, the 59 to 61 has to go first. It makes sense to go from smallest up to largest. The second is there's no connection from one color to the next here in the categories. But in numbers, there is a connection. 61.9 goes right up against the 62. So having the bars tight together hits that psychological thing we talked about of there is a connection between the data, so it creates that psychological connection by putting the bars side by side like that. There's some other reasons for it, but we're not going to get into the big details for it. And we can have circle graphs and stuff like that again, but we've covered those once for the categorical. So we're going to jump now to another one. It's a different type of data. What we were looking at up there is classifications. We're putting people into classifications, comparing multiple categories, different sections of height, different classes of height, different colors for favorite color or whatever. Now what we're going to do is we're actually going to compare one item as it changes over time. That's called a time series set of data. So rather than, say, giving a person several choices or measuring several characteristics, we're only giving one characteristic and we're measuring what that is over time. Like I might look at cost of tuition for WITC and compared to the year. Let's say in the year 2000, tuition was $98 per credit. Say in 2005, it had gone up to $111. 2010, it had shot up to $162 a credit. And in 2015, let's say it went back to $155 a credit. So the graph that I would make to represent this is called a line graph. So in a line graph, we have the year across the bottom, always. And then the other value goes up the side. Now to make this one a little more obvious, I am going to break that line. So I put that symbol in there saying I'm not counting from 0. And I'm going to start out at probably, well, I notice I'm leaving a little space underneath it. I'm going to number at 100, so the 98 is going to come in just below it. Give myself a little more clearance. So the 160 is going to come up just above that one. The 162 will be just above that. So here I'm going to graph in 2098, so just below the 100. 2005 is a 111, so just above the 110. 2000, 162, so just above the 160. And 2005, 155. Now here again is a great example. If I asked you what the price was in 2005, well, you could say it's right around 110, but you couldn't tell exactly 111. So again, the exact number, if you want it, you can refer back to a table. But what this does tell us really quickly is where the price was increasing. Between 2000 and 2005, the price increased. Between 2005 and 2010, the price increased. And between 2010 and 2015, the price decreased. It was going down. It also can tell you where the price increased the fastest. The line is steeper here, so it's increasing the fastest there. Now again, be careful, because I put the break in the graph here, it looks like this price is like 6 times as price as what it was down here, and it's not. It's roughly 1.5 times. So putting that break in the graph is risky. It does magnifies those differences, but it also makes it a little bit easier to read. Okay, with that, our next concept is to start talking about mathematical summaries of data, which I think I'm going to leave until Wednesday because I don't want to start into that with only 10 minutes left. Does anybody have questions on graphing? Okay. There is a quiz. A new quiz that is due tomorrow, Tuesday, at 11:59 p.m. And there's a new homework that is due for Wednesday. If you get to anything on that homework where it talks about mean, median, or mode, don't do it. We haven't talked about that yet. We'll talk about that on Wednesday. So if I have to extend that assignment, we will. Remember, Thursday I will not be here because I am in things over in New Richmond. But we will have class on Wednesday, and then Wednesday at the end of class we'll decide whether we're going to take the test. The 4th unit test is scheduled for Monday, but we'll decide whether we're going to take that test on Monday or push it back to Wednesday of next week. Okay, well, we'll see you guys on Monday.